Alright, so some cautions about experiments. Now, a well-designed experiment includes design features that allow researchers to eliminate extraneous variables as an explanation for the observed relationship between the independent or the explanatory variable and the response variable. Some of these features are listed below. Okay, so first off, let's start with control. Alright, control refers to the steps taken to reduce the effects of extraneous variables. I.e. variables other than the independent variable and the dependent variable. These extraneous variables are called lurking variables. Control involves making the experiments as similar as possible for experimental units in each treatment. Three control strategies are control groups, placebos, and blinding. Okay, so for the first one we will deal with is control group. A control group is a baseline group that receives no treatment or neutral, or they actually receive a neutral treatment, or in other words, they receive a placebo. To assess treatment effects, the experimenter compares results in treatment groups to results in the control group. And remember, we said in the first lesson on experiments, we actually talked about the fact that if the placebo group has a lower percent change than the treatment group, then you have something right there. You have causation. Placebo is, once again, a neutral treatment, and it has no real effect, and it's usually done on the control group. Okay, so that's pretty easy. So to control for the placebo effect, researchers often administer a neutral treatment, i.e. placebo, to the control group. The classic example is using a sugar pill in drug research. Once again, the drug is considered effective only if the participants who receive the drug have better outcomes than the participants who receive the sugar pill. Okay, now blinding, and there's also double blinding. Okay, blinding, if the participants in control group know that they are receiving a placebo, the placebo effect will be reduced or eliminated, and the placebo will not serve its intended purposes. So what you need to do is not tell the control group that they are actually receiving the placebo. So that's called blinding. Now, double blinding, knowledge of which groups receive the placebos is also kept from people who administer or evaluate the experiment. This is called double blinding. It prevents the experimenter from spilling the beans to participants through subtle cues, and assures the analyst's evaluation is not tainted by awareness of the actual treatment conditions. So in other words, you're not telling the control group, and you're also not telling the experimenter. Okay, so blinding and double blinding. So blinding actually helps with biases. Okay. All right, randomization refers to the practice of using chance methods, random number tables, flipping a coin to assign experimental units to treatments. In this way, the potential effects of lurking variables are distributed at chance levels, hopefully roughly even, across the treatment conditions. And remember, the more people you have, the better off you're going to be with randomization, because the more people you have, the larger randomized group you have, the larger randomized numbers you have, and thus you should be really close to the nice percentages that come with probability. Okay, and replication. Replication is huge because doing the experiment more than once, in other words, assigning it to more experimental units than just one group. Okay, in general, the more experimental units in each treatment condition, the lower variability of dependent measures. Okay, so that's huge things just to work for when you're just working with this. All right, now finally, confounding variables. Confounding occurs when the experimental controls do not allow the experimenter to reasonably eliminate plausible alternative explanations for an observed relationship between an independent and dependent variable. Alright, so for example, a drug manufacturer tests a new cold medicine with 200 participants, 100 men and 100 women. The men receive the drug and women do not. At the end of the test period, the men report fewer colds. This experiment implements no controls. As a result, many variables are confounded, and it is impossible to say whether the drug was effective. For example, gender is confounded with drug use. Perhaps men are less vulnerable to a particular cold virus circulating during the experiment, and the new medicine has no effect at all. Or perhaps the men experienced a placebo effect. This could be strengthened with few controls. Women and men could be randomly assigned to treatments. One group could receive a placebo with blinding. Then If the treatment group, the group getting the medicine, has sufficiently fewer colds than the control group, it would be reasonable to conclude that the medicine was effective in preventing colds. And just so you know, just working with that stuff, if you can find a cure for the common cold, fantastic. You know, you would be the world's first trillionaire, I think, if you could hold on to that patent. But anyways, confounding variables are made when you don't account for these up here. In other words, you don't replicate, you don't randomize, and you don't have control over your actual experiments. Okay, so you need to take time to be cautious about your experiments, and you need to design it well and come up with a plan. Okay, that's it for today. I'll talk to you guys later. Bye.